This video introduces one of the main features of 2D target object recognition, namely placement correction, and explains how to configure relevant parameters using the 2D target object recognition tool. In some high-precision assembly scenarios, even with 3D vision-guided picking, the target object may shift slightly after being picked. This can be caused by the gripping force of the fixture or inertia during movement, resulting in deviations between the actual pose of the object and the pose recognized by 3D vision. Therefore, before assembly, it's necessary to use a 2D camera to accurately recognize the object's planar position and orientation for placement correction. This ensures precise placement of the object and enables high-accuracy assembly. Next, using sheet metal placement correction as an example, this video shows how to configure the workflow for supporting subsequent robot assembly tasks. In this scenario, the recognition workflow consists of 4 steps: image preprocessing, target object recognition, target object pose calculation, and general settings. During image preprocessing, color space conversion and separation are used to adjust the color and brightness of the image, highlighting the features of the target object. Enhancement and denoising operations can also be applied to improve recognition performance. For object recognition, set the region of interest and adjust recognition parameters with 2D template matching to accurately recognize the target object. After recognition, use the 2D camera's extrinsic calibration data, reference object teaching information, and placement target information to convert the recognized 2D pose into the 3D pose for robot placement. This ensures high-precision placement and assembly. In the general settings, configure pose filtering rules and output ports. These configurations help meet the requirements of subsequent assembly processes. Next, let's move on to the configuration workflow. Before starting the specific operations, complete 2 preparations: placement target teaching and 2D camera calibration. Let's begin with placement target teaching. This step is essential for achieving high-precision assembly. The placement target refers to the specified assembly position. In this scenario, the target object needs to be inserted into a locating pin, so the pin is the placement target. The teaching process is as follows. First, manually insert the object fully into the locating pin to ensure it's in the ideal assembly state. Then, move the robot so that the gripper reaches the intended pick point of the target object and fits snugly against its surface. Please note that the object's pose must remain unchanged during both the teaching and subsequent recognition processes. Therefore, ensure that the gripper can securely pick the object during the operation. Once the object pose is stable, record the current robot flange pose as the reference pose for placement. This pose will be used as the reference for subsequent placement correction calculations. After teaching is completed, move the robot to the image capturing point of the 2D camera, and proceed with the software operation. Open Mech-Vision. Complete the 2D camera calibration. Make sure the camera can capture images normally, and that the image quality meets the required standards. For this scenario, it's recommended to increase the exposure time in the image acquisition settings. This adjustment allows the pixel values of the target object to approach 255. The setting helps eliminate surface texture interference, which makes it easier to use the high contrast feature of white background with black holes for positioning. As a result, the circular hole edges can be extracted precisely to meet the requirements for high-precision assembly. Next, find the 2D target object recognition step in the graphical programming workspace. Click Config Wizard to enter the tool interface and start the recognition process. Choose the appropriate usage scenario based on the scene description. For this case, select Placement Correction. The current scenario uses a fixed placement target. This means the position and orientation of the placement target remain unchanged during operation. Thus, select Fixed Placement Target. Click OK to begin the configuration. The first is image preprocessing. The current image basically meets the requirements. The object features are clear, with only a few low brightness noise at the end. Denoising can be performed through image preprocessing. In this case, linear transformation in image enhancement is preferred. This transformation applies multiplication and addition to the grayscale value of each pixel. Thus, the contrast between light and dark in the image is increased, making the object edge contour more distinct. In this case, the noise at the end already have high grayscale values. Applying linear transformation will brighten the entire image, and the low brightness noise will also become brighter, making them less visually noticeable. Compared with common filtering denoising methods, linear transformation avoids structural smoothing, which prevents additional blur. This helps maintain the clarity and stable localization of features like circular holes. In this example, simply set the scale factor to a value greater than 1 to increase the pixel intensity. Since the overall brightness of the current image is high, no need to adjust the pixel value offset. Click Run Step to check the processing effect. It can be seen that the image becomes a little brighter overall, with no obvious dark spots, and the quality meets the requirements. Then, click Next to proceed to the object recognition. First, set the recognition region. When the sheet metal part is picked to the image capturing point, it remains within a fixed area despite slight angle variation. Therefore, define a custom recognition region and set an appropriate ROI to enhance recognition efficiency. When selecting the region, sufficient margin should be left on all sides to accommodate possible changes in the object's pose. Next, generate the object template. This step ensures automatic searching and localization of objects in the image that match the template features. Click Edit to enter the 2D template editor. The image is acquired automatically, and the template can be named as needed. Select the feature region to quickly generate the template. Assembly positioning in this scenario relies on aligning the central hole of the sheet metal part with the locating pin. The circular hole serves as the key reference for positioning, and its edge features directly affect the assembly result. When generating the template, the circular hole edges should be used as the main features. An object with a clear hole edge and no obvious distortion is preferred. When drawing the template, the circular ROI tool is recommended for selecting the central hole. The selection tool can be used to adjust the ROI position and size. The selected region should be slightly larger than the feature contour to ensure complete extraction of edge features and improve positioning accuracy. After region selection, the system automatically generates the object center point, which is generally kept as default. Then, generate the template and check the extracted edge features. Adjust feature parameters as needed. The extracted template shows a continuous and complete edge for the circular hole, with no obvious breaks or noise interference. The quality of the edge extraction meets the requirements, so further optimization by adjusting the edge threshold is not necessary. For more details, refer to the documentation if needed. In this scenario, the incoming target object may exhibit a wide range of pose angles. To ensure correct recognition for objects at different rotation angles, increase the angle search range. The scale search range sets the possible size variation of the object relative to the template. Since the object size is stable and there is no significant scaling, this parameter can remain at its default value. Then, save the template. Click Update to apply the latest template configuration. Select the generated template. Click Run Step to check the recognition result. The current green matching points cover the entire feature region, showing good recognition performance. The confidence score in the recognition results is also high, so no further parameter adjustment is needed. Click Next and start to calculate the object pose. Complete the teaching process according to the operation instructions and the required pose values. In most cases, the eye-to-hand scenario is recommended. First, select the 2D camera step with completed extrinsic calibration to ensure the calibration data is correctly applied. Since the target object is already at the image capturing point, Click Acquire to obtain the 2D pose of the reference object. Then, click Edit and enter the robot flange pose at the image capturing point. Next, locate the reference pose for placement recorded during preparation. Click Edit and enter this pose. Now, the teaching process for the eye-to-hand scenario is complete. Click Run Step to view the 3D pose required for placing the object in the recognition results. During subsequent operation, the system calculates the deviation between the actual 2D pose and the reference 2D pose of the object. This deviation is converted to the robot coordinate system based on the calibration parameters and applied to the placement pose, enabling high-precision assembly. Click Next to proceed to the general settings. Before configuration, use Run Step to confirm the current recognized pose of the target object. Configure pose filtering rules and output ports according to actual requirements. Pose filtering is mainly used to exclude poses that may present collision risks or cannot be executed. For this scenario, this parameter does not need to be enabled. Adjust settings according to the actual situation on site. Please see the documentation for more information. For output ports, the system will output the object name and recognized pose by default. To evaluate matching quality, please select the Matching Score port to output a list of matching scores. Click Save. Return to the project interface. At this point, the 2D object recognition configuration for sheet metal placement correction is complete. Next, connect the output step to check the overall operation. In this scenario, the point cloud model matching is not needed to acquire pose. So, according to the instruction of Select Scenario, select Depalletizing and others. After scenario selection, set the target object. Open Target Object Editor, select For Picking. Select No Point Cloud Model Required in Select Configuration Workflow. After entering the interface, save directly without making any changes. Then, under Target Object Without Point Cloud Model, select the object you just saved. Next, since collision detection via point cloud is not required, uncheck the point cloud settings in the Collision Detection settings. Other ports can be configured as needed. Connect the corresponding step ports and run the project. The pose recognized by this tool is the placement pose after placement correction and compensation. This pose can be sent directly to the robot, guiding precise placement of the object. For more information on 2D object recognition applications, refer to subsequent tutorial videos and related documentation.